Okay, so um, let's just go through the other methods for finding gradients. Another standard method that people might use to compute gradients is a finite difference approximation, um, also called numerical differentiation or the method of divided differences. And the idea is really simple. It goes back to how all of you learned what means a derivative, right? So if you have a function f of p that is a real number, and p is a couple of variables here, each of which is a real number, in other words p is an R2, then the derivative, the partial derivative of f with respect to p1 is you take f, perturb p1, like add a small number h to p1, evaluate the function there, and then subtract that function value from the function value at p1, p2, and divide by h, right? So that's really what we mean by the slope of a function. This kind of approximation of a partial derivative is called the forward difference approximation because you're stepping forward in the parameter value. You can instead do f of p1 p2 minus f of p1 minus h p2 divided by h. That would be called a backward difference approximation of the partial derivative. Of course, you can do the same thing for p2, right, by perturbing p2, etc. There's something called the central difference approximation, which steps forward and then backward and then divides by 2h. They're all approximations to the derivative. Now, I can post a link to the technical aspects of how accurate these things are in more detail, but let me just make some brief remarks here. Of course, if you can evaluate the function f of x arbitrarily accurately, then taking h going to 0, right, taking as small a step as possible, will make this quantity, this ratio, go to the limit of the derivative, right? So the derivative estimate will be more and more accurate if you take h closer and closer to 0. In fact, that is literally how we define the derivative. The derivative is the limit of this ratio, right, in the mathematical sense. Okay, but that turns out that sense in which this goes to the derivative, this ratio goes to the derivative as h goes to 0, is true only in the strictly mathematical sense when f can be evaluated to infinite precision. But if f can be evaluated only to finite precision, in other words, there is an error in your evaluation of f, and of course any numerical evaluation of f will have a small error because we always operate with finite precision in general. This ratio will not converge to the derivative if you take h goes to 0. In fact, if you make h too small, this estimate will diverge, will sort of go to infinity or do some crazy thing. Okay. So it turns out if we can evaluate f to infinite precision, taking h to 0 is the right thing to do, having a really small h. But in practice, if you're using it to evaluate numerically the derivative, too high or too low an h value will yield bad derivative estimates. Okay. And here's the thumb rule for how big h should be. If epsilon is roughly the error in evaluating f, right? If epsilon is the error in evaluating f, then h, it turns out, should be square root of epsilon if you're using the forward or the backward difference formula, and cube root of epsilon if you're using central difference formula above. If you have a very simple function like we've discussed, your function accuracy is about error is about 10 to the minus 15 or 16, because you have 15, 16 decimal places for significant digits. Roughly, your mission EPS is about 10 to the minus 16. So if you have that, then let's say 10 to the minus 16, then if you are using the forward difference formula, you should use epsilon of about 10 to the minus 8 to get the best possible accuracy for your derivative. But if you're using central difference formula, you should use about 10 to the minus 5. Okay. Cool. So the intuition for why you should not use too large an h or too small an h is as follows. Let's say this blue curve is the actual function, and then this magenta curve is the function evaluated through a numerical process. Just sort of exaggerated noise here, just to illustrate the idea. If you take too large an h, like let's say you take an h from here to here or something like that, then you will basically miss this curvature in the function. The curvature will affect your estimate of the gradient, right? So if you take too large a step, you will not be able to get this slope, but you will get basically this slope. Let's say you want to evaluate the function gradient or the slope here. If you take too large a step, then you will obviously get a wrong gradient value. So too large is bad. If you take too small an h value, then because of this sort of noisiness or the inaccuracy, you will essentially be differentiating the noise. Like noisy curve might be wiggly, and you'll be differentiating the noise, and you'll get again a bad value for the derivative or the slope. But ideally you want some good h which sort of steps over the noise, but not too much, so that the function itself is okay. Okay, so let me actually close this, because that seems to no longer be in sync with my voice, my face. Okay. Yeah, so it turns out that having using these h values will result in a derivative error of about square root of epsilon if you have forward or backward difference, and then derivative error of epsilon power 2 by 3 for central difference. So if you have 10 to the minus 15 epsilon, then if you use forward or backward difference, you get 10 power minus 7.5 as the error on the derivative, and then you get about 10 to the minus 10 if you use central difference as the derivative error. So ideally one should use central difference because it's more accurate, but forward or backward difference is often used because it usually uses fewer function evaluations. If you're anyway evaluating the function at the current p, you have to do one more function evaluation to estimate the derivative. But if you're anyway evaluating the function at p, you have to estimate more function evaluations to do the central difference approximation. So people often use forward difference approximations or backward difference approximations to estimate the derivative. So an important takeaway is that these finite difference approximations reduce or don't have as accurate a function derivative estimate as possible, because if the function is evaluated at 10 to the minus 15, the derivative is evaluated only to about 10 to the minus 7 or 8 accuracy. So the accuracy dramatically decreases. So it's not the most accurate method, say compared to analytical derivative estimation. Also, it turns out that it requires additional function evaluations, and it turns out there are other methods that are more accurate but also more efficient in terms of computational efficiency. Okay, so that's the next topic, which is called automatic differentiation or algorithmic differentiation, which is the modern standard for doing derivative estimations, especially in the machine learning world.